June 28, 2015, 139 seconds after liftoff. A tiny puff of white vapor appears on SpaceX's Falcon 9 rocket, streaking toward space. Within milliseconds, the second-stage oxygen tank ruptures from the inside out. The booster disintegrates into a massive fireball at 25,000 miles per hour. Inside the exploding wreckage is $110 million worth of critical cargo, food for astronauts, the first docking adapter for future crewed missions, Microsoft HoloLenses, and supplies from 30 student experiments. All of it vaporized. And the culprit? A $2 steel strut that failed not from being underrated, but from a manufacturing flaw in a specific joint. This wasn't a complex engineering failure. This wasn't a freak accident. This was a design oversight so basic that the official investigation determined a faulty structural joint within the strut led to its catastrophic failure. One cheap part, installed without proper testing, nearly destroyed SpaceX's reputation and grounded the entire Falcon 9 fleet for months. This is the story of how SpaceX's obsession with saving money by using off-the-shelf parts led to a disaster. How a strut designed to withstand immense force failed prematurely. How the Dragon capsule survived the explosion but drowned in the Atlantic because nobody programmed it to deploy parachutes. And how Elon Musk had to stand in front of cameras and explain that thousands of engineering hours couldn't prevent a disaster caused by a vendor-supplied component failure in a rocket that cost tens of millions to build. Before CRS-7, SpaceX had completed 6 consecutive successful resupply missions. They were unstoppable. After CRS-7, they had to prove they could be trusted again. By June 2015, SpaceX was on a winning streak. 6 successful cargo missions to the International Space Station. The Falcon 9 had become NASA's workhorse for delivering supplies. Wall Street was bullish on commercial spaceflight. SpaceX was valued in the billions, and CRS-7 was supposed to be routine, just another milk run to the ISS. Except this mission carried something irreplaceable, the first international docking adapter. IDA-1 was critical for the future of American spaceflight. Since the Space Shuttle retired in 2011, NASA had been paying Russia hundreds of millions of dollars to send astronauts to the ISS. The Commercial Crew Program, Boeing and SpaceX's new spacecraft designed to carry humans, was supposed to end that dependency. But those vehicles needed new docking systems. The old berthing ports wouldn't work. IDA-1 would convert the ISS to accommodate the new generation of crew capsules. Without it, the entire commercial crew timeline could slip by years. The cargo manifest was packed with other critical items: modified Microsoft HoloLenses for augmented reality experiments in space, a new spacesuit to replace one that had partially failed on the station, food, water, and crew supplies worth months of reserves, and experiments from 30 student teams who'd spent years designing research for microgravity. This wasn't just cargo, it was the future of NASA's spaceflight program and the dreams of hundreds of students. SpaceX also planned something ambitious, their third attempt to land the Falcon 9 first stage on the autonomous drone ship. Previous attempts in January and April had failed, but SpaceX was getting closer. If they could nail the landing, it would prove that reusable rockets were possible, slashing launch costs and revolutionizing spaceflight. Everything was riding on CRS-7.
June 28, 2015, 10:21 a.m. Eastern Time, the Falcon 9 lifts off from Cape Canaveral, climbing through a perfect Florida sky. For the first 2 minutes, everything looks nominal. The 9 Merlin engines roar at full thrust. Telemetry shows green across all 3,000 sensors. The rocket passes through max Q, the point of maximum aerodynamic stress, without issue. First stage separation is seconds away. Then, at T plus 139 seconds, Mission Control sees it. A small white cloud appears near the second stage. In the SpaceX control room, alarms start screaming. Telemetry shows a catastrophic pressure spike in the liquid oxygen tank. The entire failure happens in 0.893 seconds, less than 1 second from first warning to total vehicle breakup. There's no time to react, no time to troubleshoot, no time to save anything. The Falcon 9's flight computer detects the failure and activates the flight termination system, essentially self-destructing the rocket to prevent it from flying uncontrolled and crashing into populated areas. The booster completely breaks apart, tumbling through the sky in pieces. On the live stream watched by thousands, the rocket transforms from a precise spear climbing toward orbit into a chaotic cloud of debris falling toward the Atlantic. But something incredible happens. The Dragon capsule, designed to survive a launch abort, ejects cleanly from the exploding rocket. It keeps transmitting data as it tumbles through the air. Engineers watching the telemetry realize the capsule is intact, structurally sound, falling toward the ocean. If the parachutes deploy, they could recover it. The cargo could be saved. But the parachutes never open. The software controlling Dragon wasn't programmed to handle this scenario. SpaceX officials later admitted the capsule could have been recovered, but they hadn't included abort logic in this version. The Dragon hits the ocean at terminal velocity and disintegrates on impact.
Within hours, SpaceX established an accident investigation team. NASA's Launch Services Program designated their own independent review team to provide oversight. The FAA grounded the entire Falcon 9 fleet pending investigation results, and Elon Musk, never one to wait for official reports, started tweeting his theories. There was an overpressure event in the upper stage liquid oxygen tank. Data suggests a counterintuitive cause. The investigation was brutal. SpaceX engineers spent thousands of hours analyzing over 3,000 telemetry channels, frame-by-frame video footage, and recovered debris from the Atlantic. They used Higgs editors to recover data from the final milliseconds before breakup. The pressure was enormous. Every day the Falcon 9 remained grounded, costing SpaceX money and credibility. Competitors whispered that commercial spaceflight was too risky. Traditional aerospace contractors lobbied Congress to defund the Commercial Crew Program. On July 20th, 2015, less than a month after the accident, Musk held a press conference to announce preliminary findings. SpaceX had identified the culprit, a steel strut inside the second-stage oxygen tank. These struts held down high-pressure helium bottles, called composite overwrapped pressure vessels or CPOVs, that pressurized the propellant tanks during flight. One strut failed catastrophically, liberating a CPOV that smashed through the liquid oxygen tank like a wrecking ball. The tank ruptured, oxygen poured into the engine bay, and the entire stage exploded. But here's where it gets embarrassing. The strut failed because a missing or incorrectly installed structural pin within its joint allowed the assembly to buckle under flight loads. Closeout photos taken during stage construction showed no visible flaws or damage. The strut looked perfect. So what happened? SpaceX officially concluded it was a sub-assembly component failure from the vendor that introduced a fatal flaw.
The SpaceX FAA investigation report was officially released in December 2015. However, NASA's independent review team raised its own significant concerns. The public summary of these concerns, which was released later, was damning. NASA didn't just blame a manufacturing defect, they blamed a design oversight by SpaceX. And the language was brutal for a government agency that usually speaks in diplomatic euphemisms. NASA determined that SpaceX had not adequately tested the struts in the combined cryogenic and load environments of flight, and questioned the overall application of the part, overlooking the manufacturer's safety margin recommendations. The report further noted that the type of strut used was considered precipitation-hardened stainless steel and should have been subjected to greater scrutiny. This was a devastating finding. It meant the failure wasn't bad luck. It wasn't a one-in-a-million manufacturing defect that nobody could have predicted. It was a preventable mistake caused by cutting corners on part selection and testing. NASA's report essentially said SpaceX knew better, or should have known better, and chose wrong anyway. SpaceX's entire business model was built on disrupting traditional aerospace by using commercial off-the-shelf components instead of expensive space-certified parts. Why pay $10,000 for a custom aerospace-grade connector when a $100 commercial connector does the same job? Why use proprietary serial bus cables when modern Ethernet works fine? SpaceX famously used toilet stall handles as latches on Dragon storage lockers. This strategy slashed costs and made SpaceX the cheapest launch provider on Earth. But CRS-7 revealed the limits of that approach. Some components can't be cheaped out on. One observer noted SpaceX's cost-cutting strategy might have been pushed too far before the CRS-7 failure. A $2 strut in a critical load path isn't the place to save money. Not when failure means losing $110 million in cargo, grounding your entire fleet, and potentially killing the commercial crew program. The Falcon 9 failure destroyed cargo valued at $110 million, according to NASA, including the first docking adapter for commercial crew vehicles. The docking adapter alone set back NASA's plans by years. A replacement IDA wouldn't reach the ISS until 2016 on CRS-9. But the financial damage went beyond the lost cargo. SpaceX had to conduct an extensive investigation, implement design changes, add new testing protocols, and prove to NASA that they'd fixed the problem. The Falcon 9 was grounded for months. To compensate NASA, SpaceX agreed to discounted prices for several later missions in December 2015. They negotiated a contract modification that gave NASA additional capabilities at no increase in cost. SpaceX essentially paid for their mistake by slashing future profits.
SpaceX moved fast to regain trust. They eliminated the problematic strut design entirely, redesigning how COPVs were secured inside propellant tanks. They implemented load testing for all critical structural components, even off-the-shelf parts. They added new quality control screening for vendor-supplied hardware, and they created processes to ensure proper safety margins were maintained for every component, not just the obviously critical ones. The changes went beyond hardware. NASA sent SpaceX a letter in February 2016 expressing concerns about the company's systems engineering and management practices, hardware installation and repair methods, and telemetry systems. SpaceX had to demonstrate they'd matured as an organization, adding processes and oversight that startups typically resist. By January 2016, SpaceX was ready to fly again. The Jason 3 Earth observation satellite launched successfully on a Falcon 9 V1.1, which included the necessary design fixes. In April 2016, SpaceX returned to ISS resupply missions with CRS-8, successfully delivering cargo and landing the first stage on the drone ship. The nightmare was over. SpaceX had proven they could learn from catastrophic failure and come back stronger. One haunting detail still bothers SpaceX engineers. The Dragon capsule survived. Video analysis and telemetry confirmed the capsule separated cleanly from the exploding Falcon 9. It was structurally intact, falling toward the ocean in a controlled manner. If the software had been programmed to recognize the abort scenario and deploy parachutes, engineers believe Dragon could have been recovered with most cargo intact. SpaceX officials publicly stated recovery would have been possible with proper abort logic, but the CRS-7 Dragon was a cargo version without the sophisticated launch escape system of the Crew Dragon. Nobody had programmed it for this specific failure mode. The assumption was that if the rocket failed catastrophically, nothing would be recoverable anyway. That assumption cost NASA the docking adapter and 30 student experiments that might have survived. After CRS-7, SpaceX updated Dragon's software to handle more abort scenarios. They added logic to recognize various failure modes and deploy parachutes if the capsule survived separation. Future cargo Dragons would be smarter, more autonomous, capable of saving themselves even when the rocket couldn't. It was a lesson learned in the worst possible way. CRS-7 was SpaceX's second major launch failure after 3 Falcon 1 failures nearly bankrupted the company in 2008. But this one was different. In 2008, SpaceX was a scrappy startup trying to prove rockets could work. In 2015, they were an established company with a NASA contract, Wall Street valuation, and reputation for reliability. The 2008 failures were expected growing pains. The 2015 failure was inexcusable. Musk later admitted the success of previous launches had created complacency. He said during a press conference, "We had had 6 successful missions in a row. Success can breed complacency, and we absolutely were becoming a little bit complacent." CRS-7 shattered that complacency. It reminded SpaceX that spaceflight is unforgiving. One bad decision, one cheap part in the wrong place, and everything explodes. The investigation also revealed cultural issues. How did a strut with a flawed joint end up in a critical load path without proper testing? Why didn't anyone question whether a component designed for factories should fly on a rocket? Where were the engineering reviews that should have caught this? These were systemic problems, not isolated mistakes. SpaceX had to mature from a startup mentality to an aerospace discipline that treated every component as mission critical. Today, SpaceX has flown over 400 successful missions since CRS-7. The Falcon 9 has become the most reliable rocket in history. They've landed and reused boosters hundreds of times. They've sent astronauts to the ISS. They've built Starlink, the world's largest satellite constellation. And they did it all while implementing the lessons learned from a $110 million failure caused by a $2 part. The CRS-7 mission's total economic loss, including the rocket, cargo, and subsequent grounding costs, is estimated to have exceeded $133 million. But the real cost was trust. NASA had bet billions on commercial spaceflight. Congress was skeptical. Traditional aerospace contractors were lobbying to kill the program, and SpaceX had just handed them ammunition. But here's what's remarkable. NASA didn't abandon SpaceX. They worked with them to fix the problems, they accepted the corrective actions, and they continued awarding contracts, betting that SpaceX would learn from failure rather than repeat it. That faith was justified. By 2025, SpaceX had completed over 30 successful cargo missions, revolutionized spaceflight with reusable rockets, and become NASA's most reliable partner. The CRS-7 failure taught SpaceX that disruption has limits. You can challenge traditional aerospace on manufacturing methods, business practices, and cost structures, but you can't cut corners on critical components. You can't assume commercial off-the-shelf parts will work in extreme environments without testing. And you can't let success breed complacency when you're strapping millions of dollars of cargo to a controlled explosion. 1 flawed steel strut. $2. Catastrophically failed at a critical moment, 139 seconds into flight. $110 million destroyed, 6 months grounded. And a lesson that SpaceX would never forget. In spaceflight, there's no such thing as an unimportant part. Everything matters, everything can fail. And when it does, the consequences are measured in millions of dollars and years of setbacks. That's the real story of how the CRS-7 mission became SpaceX's $110 million failure.